Hi, and welcome to the first video in a series of videos for our data structures class. We'll start out talking about a data structure that you've probably already used and are probably somewhat familiar with. The lowly, meaning it's a very low-level structure, low-level array. It's simple, but it's a very useful collection class, and that's exactly what we'll talk about here. We'll also introduce some terminology when talking about arrays that you probably haven't used to describe these things before. Now, I'm assuming you already know a lot about arrays in terms of the big picture. You probably used arrays in Java like this example. Now, I might have the syntax wrong on the my array there because I'm notoriously bad in Java array syntax. But the idea is that you're creating a array with 20 elements. The nice thing about arrays is that they're really fast in terms of big O notation. Now, we've been struggling to understand what big O notation implies, but it implies here that read writes updates are O1. That means that you can use an index and go directly to the needed element with no further searching. So access to the array is does not depend in any way on the number of elements in the array, at least not accessed by the index. So it's O1. Inserts and deletes, we'll find out, are much more problematic, and we're going to come back to that, but they're not going to be O1. We're also only addressing one-dimensional arrays here, but the analysis is, it's easy to generalize to 2D as well. Now, arrays have a wide variety of applications. You've probably applied them in a number of projects that you've done. They're a good fit for applications that perform identical or very similar calculations over a large number of variables. In other words, multiple elements. So you can have arrays and loops go hand in hand. Loops drive you through processing all or some of the elements in the array, and the access to those elements is very quick. Examples that just off the top of my head include filtering, those applications that have sample data, let's say, in a series of integers or a series of floating point numbers, and you need to do some kind of filtering on that, as in filtering an audio signal or filtering a data series that represents time series that represents stock market data. And that's usually done by computing a running average or a running median of some kind, meaning taking a few successive values in the array and performing some operation on to summarize them, and then maybe sliding over one element and performing the same operation again. It's almost recursive. And this is a very, very common application, say, in engineering and in data science. Data smoothing, which is done a lot in data science, is the same sort of thing. If you need a fixed size lookup table, so you just want to be able to convert a numerical value into, let's say, a character label, a name of a particular game character who's otherwise referred to only by number, arrays are very good for that. And arrays are also used widely as the underlying, the base implementation of many higher level types, such as strings. String, which has a lot of interesting behaviors at a high level, and it's very user friendly. You can concatenate and search and all those kind of things. That ultimately is implemented, at least in C++, in terms of character arrays. So they're extremely important, even in more complex data structures. Now, arrays are fast to read and write and update because of address calculation. And what does address calculation mean? That means it's really easy for the compiler or the interpreter to figure out where in memory the desired location fits, and then to be able to go directly to that element. For instance, all you need to know is where the address starts and how big each element is. So you can compute the address of the fifth element, for instance, by taking where the array starts and adding 5 times the size of element. That turns out to be very little machine code. It's just 3 or 4 instructions. So it runs very fast. So that's the really big advantage of arrays is fast as in actually fast and fast as in logically fast, O1, when it comes to getting to specific elements. Here's a picture. So let's look at this. And this shows, I know you've seen these for arrays before, but let's look through this and think about what it means. The numbers on the top, this I'm calling this a vanilla array. I mean, that's not a technical term, but it's commonly used in programming to describe something that's unadorned or unembellished. And later on, we'll talk about what I'm calling fancy arrays. Again, not a technical term. In this array, this plain array, the top row of numbers, 0, 1, 2, a big space, and then 19, those are the indexes. I probably should say indices grammatically, but no one says that, so we'll say indexes. They start from 0, for historical reasons, and because that simplifies a little bit that calculation I showed on the previous slide, where that address calculation. The values in the gray boxes are pretend integer values that I just have put in there. There's 52, 77, 13. I've omitted drawing a ridiculous number of boxes, and it ends the last element, which is index 19, has a 91 in it. The third row of numbers along the bottom, 400, 408, 416, up to 560, those are pretend machine addresses for this array. So if the array really could start at address 400, then the next element after the 0th element, the next element after that, the 1th element, would be at 408, assuming it enters 8 bits, and then 416 and so forth and so on. So the I'm assuming this array has an extent or size of 20, and there's functions in every language that will give you the size of the array. So access to any of those elements, as you can see, is O1. You go directly to them. If you want to search for an element, because you don't know the index, but you're going to search by value, you're going to use the numbers in the boxes rather than the indices across the top. That's about worst case ON, order in, because as you add more elements, you have to search farther and farther and farther before you find the one of interest. I think you know this stuff already, albeit not possibly in these terms. In order to achieve that behavior that we're talking about, we have to impose some constraints on arrays. And maybe when you used arrays, you didn't even think about these constraints. But for this super fast access to work, the elements have to be stored contiguously. That is, they have to be adjacent to one another, side by side, in memory with no space in between. Because the calculation of where each element lies in memory won't work if they're not on element-sized boundaries. Also, that all the elements are the same size. If you think about it, sticking different sized elements in there, even if they were contiguous, would render that address calculation useless, because it wouldn't land in the right place because some elements are much bigger than others. That all leads to the idea that we can, and this is the part that you probably haven't ever thought about arrays in terms of, there's a kind of meta language we're going to employ in this class. In other words, a language for talking about data structures. It's pretty abstract, but it's actually useful. So I'm going to read it to you, and then I'm going to explain why I think it's useful, and then we're going to unpack it, explain it on the next slide. Arrays are, plain arrays, a fixed sized indexed collection of identically sized objects using integral keys stored contiguously. Now, that's a mouthful. However, if you memorize that definition, then sometime if you're ever asked to explain, hey, tell me how arrays work, you can refer to that and think about all the points you have to hit. Oh, well, they have arrays have indexes, and those are numbers that tell you which allow you to directly access each element. They've got to be all the same type. It can't be different types, because so an array has to be an array of integer or array of float or array of object. Using integral keys, we'll come back to that in a minute, but if you think about it, the index values have to be ordinal numbers. They have to be counting numbers, 0, 1, 2, 3, 4. You can't have a fractional index. And stored contiguously, well, we know that because most of the important performance boosts and gains we're going to get from using arrays all depend on them being in the same chunk of memory side by side. Okay, back to the definition. Let's unpack it. Usually arrays are treated as fixed size. Now, it's possible to grow and shrink arrays, but that takes us out of the realm of O1 style performance and into much slower OL or more complex operations, which would tend to be slower. If you think about it, it might not be too hard to insert an element at the end of an array. Just grab a little more memory. If there's memory available, maybe there's some unused elements at the end of the array, you can just use them, and that's O1. But if you wanted to insert an element in the middle of an array, you would have to slide all the elements to the right of that array over one position, or however many positions you're inserting. If you want to delete, you'd have to slide all of the remaining elements over left one position. That sliding is a bunch of copying in memory. Now, because those elements are stored contiguously, your CPU can copy them pretty quickly, but it does take a significant amount of time relative to just going directly to that element and changing the value. So we'll come back to the issue of growing and shrinking arrays, but essentially there's some data structures that make that easy for you. In Java, if you used an array list already, not just an array, but an array list already has methods built into it as class that allow for inserting, deleting, and even sorting elements. Although the performance there will be significantly less than when you're just accessing the elements. Okay, so that's kind of what the first part. If you contiguous storage, we just talked about this a little bit, it's important because address calculation, which is fast, is not going to work or be a heck of a lot more complex if the elements varied or scattered around in memory. They've got to be right next to one another. Collection is a term, and I know you've heard this in your Java classes. Collection is a term that means a container that has more than one element. It's an aggregate type. So an int is an int, one int. It's a scalar. But an array of ints is a set of integers with presumably more than one. So we're going to talk about a lot of collection classes. Java has many and calls them this. Python has implicitly several very useful ones, and we'll come back to that. And with a moment's thought, you'll see that indices have to be whole numbers. You can't go via address calculation to the 7.5 index. That's in the middle of some element. Doesn't make sense. So coming up in the next video and in subsequent work in the class, we'll look at how these things can be generalized a little bit. So that's a quick summary using the data structures perspective of something you probably already knew and some things you might not have known about plain vanilla arrays. As we relax the constraints and we get more flexible features and behavior, but performance begins to degrade. There's always a trade-off between features and performance. Vanilla arrays have very few features and high performance. Python lists and Java array lists are really two kinds of classes, if you will, that wrap arrays in a more user-friendly, flexible, functional object wrapper. So they let you do a lot of things that are difficult to do manually or with inline code with regard to plain arrays. I would say, you may or may not like this analogy, maybe you'll get tired of it, maybe I'm tired of it. If we've been discussing vanilla arrays, that is arrays that are plain and unadorned, then the Python list and the Java array list are more like fudge ripple ice cream than vanilla. Yeah, I know it's bad, but they have lots of extra features that are not present in the plain vanilla version. So that's one way of thinking about it. We'll explore this sort of generalization, how you get these extra behaviors and how they work in the next video. Thanks.